Have you ever just stopped and wondered, what is a thought? I mean, physically, or how does your brain actually create a feeling like joy or sadness? Well, today, we're going to take a journey. We're going deep inside the most complex machine in the known universe, the human brain, to really get a look at the biological machinery behind every single thing we think, feel, and do. We're about to explore the very wiring of consciousness itself.
And this quote right here, this is our starting point. It's really the core idea for this whole deep dive. Every single thought you have, every memory you pull up, every decision you make, it's not happening in some abstract, cloudy space. No, it's happening right now in the physical, biological hardware that's sitting right between your ears.
And what is that hardware made of? Well, for the most part, it's made of neurons, or nerve cells. And the sheer number of them, it's just staggering. We're talking about roughly 100 billion of them, packed inside your skull. Now, to put that into perspective, that's more than 10 times the number of people on the entire planet, all working together in a massive symphony to create, well, you. The scale is just immense.
So, here's our game plan. We're going to start with that mind-body connection. Then, we'll zoom way in to meet the star of the show, the neuron. After that, we'll check out the electrical spark that makes it all happen, see how it jumps the gap to talk to other neurons, and then finally, we'll zoom all the way back out to see how these tiny little cells create our entire sense of self.
Okay, let's get to it. Time to meet the hero of our story, the neuron. This is the fundamental building block of your entire nervous system. It's the microscopic messenger that carries all the information that makes you who you are.
And here it is. I know, it kind of looks like a weird microscopic tree, right? But that unique shape is perfectly designed for its one big job, communication. So let's take a quick tour of its different parts.
First up, you've got these branchy-looking things called dendrites. The easiest way to think of these, they're the neuron's ears. Their whole job is to just listen, to collect all the incoming signals and messages from thousands of other neurons nearby. So once the dendrites and the main cell body collect enough information, that message gets sent down this long single cable. That's the axon. So if the dendrites are the ears, you can think of the axon as the mouth. It carries that electrical signal away from the cell, sometimes over pretty amazing distances inside your body. Now see that stuff wrapped around the axon? That's a fatty layer of insulation called the myelin sheath, and it's absolutely crucial. Just like the plastic coating on an electrical wire, it keeps the signal strong and lets it travel incredibly fast. We're talking up to 400 feet per second. And when this sheath starts to break down, like in diseases like multiple sclerosis, communication can slow down or even stop. That just shows you how vital this fatty insulation really is.
And you know, we can't talk about neurons without giving a shout out to the unsung heroes of the brain, the glial cells. For every one neuron, you've got several glial cells working as its personal support team. They're the ones making the myelin, bringing in nutrients, cleaning up waste, basically doing all the maintenance to keep the neurons firing on all cylinders.
Okay, so we know the basic parts of a neuron, but how does the message itself, that neural impulse, actually happen? This is where things get, well, electric, literally.
This message has a name. It's called an action potential. And it is exactly what it sounds like. It's a tiny but very real electrical charge. Just picture a spark of electricity zipping all the way down the axon, carrying a piece of information from one end to the other.
So to really get that spark, you need to understand the neuron's two basic states. When it's just sitting there, waiting, it's polarized. That just means there's a negative charge on the inside and a positive charge on the outside. But when it fires, it depolarizes. Tiny little gates fly open, positive ions rush inside, and that's what creates the electrical spark.
The whole process is like this beautiful, super fast four-step dance. First, the neuron is at rest, just hanging out, polarized. Then it gets enough stimulation from other neurons to hit a critical tipping point. That triggers the main event, the all-or-none action potential, the spark. And finally, there's this tiny little reset period, called the refractory period, before it's ready to dance all over again. And this brings us to a super important rule called the all-or-none law. It's simple. A neuron is like a light switch. It's either on or it's off. A neuron can't fire just a little bit. It either gets enough of a signal to fire at full strength, or it doesn't fire at all. There's no dimmer switch. The intensity of what you feel, like a light touch versus a hard push, comes from how many neurons are firing and how often, not from one neuron firing harder.
Okay, so we've got this electrical message, this spark, that has raced all the way down the axon. But here's the catch. Neurons don't actually touch each other.
There's a tiny, tiny little gap between them. So, how does the message get across? It all happens at a junction called the synapse, and this microscopic space is where something truly amazing happens. The message does a quick change act. It transforms from an electrical signal into a chemical one, just for a split second, long enough to leap across that gap to the next cell.
And here's how that works. When that electrical spark, the action potential, hits the end of the axon, it triggers the release of these tiny chemical messengers called neurotransmitters. They float across that tiny synaptic gap, and they lock into special receptor sites on the next neuron's dendrites, kind of like a key in a lock. And just like that, the message is passed along. It's this elegant microscopic relay race happening billions of times a second in your brain.
So we've been zoomed way in on a process that's almost impossibly small and unbelievably fast. Now it's time to pull the camera all the way back out and connect all this microscopic action to our actual everyday lives.
And here's the big takeaway, the thing to really wrap your head around. Every single thing you're experiencing right this second, the sound of my voice hitting your ears, the ideas forming in your mind, even the decision to maybe shift in your seat, it's all the result of billions of these tiny electrical sparks and chemical handshakes, all firing in a symphony of unbelievable complexity. And, understanding this is how we're able to develop medicines that can help fine-tune our brain chemistry, or even design things like artificial intelligence.
Which kind of leaves us with a final, pretty profound question to chew on. If the entire rich tapestry of human consciousness, love, art, science, our memories, is ultimately built from these simple, repeating biological events, what does that truly mean about the nature of the self, about who and what we really are?